before we jump forward. We said that, and I've been saying this from the beginning of the start of this class, this module, and even before that, even without an input voltage to an amplifier, there's going to be an output voltage at the amplifier, all because of movements of electrons internally in the amplifier. And an operation amplifier is no less. Matter of fact, it even exacerbates the condition even more, even further, because of its high gain. When you have a voltage, internal voltage drop, which we know as our junction potential for an amplifier, that potential voltage or that junction potential is amplified because the amplifier is an amplifier. So it's going to amplify everything. So that's going to be amplified and outputted, even though that voltage is very, very small. However, what is happening at that time is that you're going to be having an output voltage, even though you're not applying an input voltage any at all. And that, though, will offset your expected output voltage when you do have an actual input voltage. Follow me so far?
Oh, yes, sir. Yes, sir.
Good. And you should, because this is something we have been over so many times.
Sir, you said this has a specific name, right, sir?
What of a specific name?
This phenomenon.
Yeah, well, it's an offset output voltage.
Okay.
You have an offset output voltage, meaning that you have an output voltage that is going to be outputted even when you do not have an input voltage.
All right, thank you, sir.
Right. So if you look even at this page on screen, it says that recall from, well, it says chapter, but recall from previous, right? That one of the characteristics of an ideal operational amplifier is that it has zero output voltage when both inputs are zero or they are grounded. So if there are no inputs, you're supposed to have a zero output voltage. That we should know. That we do know. This characteristic is particularly important in applications where DC or low frequency signals are involved. If the output is not zero when the inputs are zero, then the output will not be at its correct DC level when the input is at DC level other than zero. So in other words, you're gonna get the output. You're right, you're gonna get the output even if you not no input, right?
Yes, sir.
And it goes further to say, and remember, students, that these are notes that are posted, so you can actually go and read them. They're there. That's why I go to the headache of finding different resource material to give you guys, to make things easier for you, right? The actual value of the output voltage when the input are zero is called the output offset voltage. So that we know by now. I would say that the output offset is very much like a DC bias level in the output of a conventional amplifier, in that it is added to whatever signal variation occurs there. So in other words, what's going to happen is you have this offset voltage that's going to add to the actual output voltage when you do have an input voltage. So it's like saying, okay, if I know that this drum is completely empty, it will take 12 5-gallon bucket to fill it. That I know for sure, right? If I know that the drum is completely empty.
Yes, sir.
However, if rain fell overnight, water, remember no, you're not putting it, you're not putting any of that 5-gallon bucket of water into the drum. It's just rain that fell overnight. and catch some water in the drum. So it means that there is consider the drum having water as your output. So it means that the drum actually has an output because it has water, right? Even before you pour one of that 5-gallon bucket water into that drum. So that is what we're talking about. It has been, the output now has been offset from from the expected 12 buckets that would, after 5-gallon bucket that would fill it, right?
Yes, sir.
So it has been offsetted, right?
Yeah. Yes, sir.
Good.
So basically, if we wanted to find the offset, the output offset amount of water, we would have to have measured how much rainwater went in there during the period.
Absolutely. Or you would have to try and get rid of the water that was in there before, so that it comes back to give you the true measurement, right? So that's what you're trying to do. You're trying to get rid of that voltage, or that you're trying to get rid of that water that is in the drum that you didn't put in there, but it's in there. That's what you're trying to do. You're trying to get the output offset voltage now to become zero. How do we get the output offset voltage to become zero? We can have two ways of doing it. We can either use, and this is what this chapter is saying, this paragraph is saying, starting at manufacturers. It says manufacturers do not generally specify output offset because as we shall see, the offset level depends on the closed loop gain that a user designs through choice of external component values. Remember, we said that what the manufacturer is making is the operational amplifier. But when you put the operational amplifier into a network, even though you know what the operational amplifier gain is, that will not be the gain of the network. We have found and proven that over the past 4 or 5 weeks. We saw that the gain, for example, of an inverting amplifier has nothing at all to do with the gain of the amplifier that is used, the gain of the operational amplifier. But it actually is dependent upon what? What's the gain of an inverting amplifier?
1 plus RF over feedback resistor over the input.
All right. Well, that tells me that you'd have failed the test today. That is called a non-inverting.
RF. Minus
over
RF.
All right. So you realize that the gain of the amplifier, in that case, is independent. The gain of the network is independent of the amplifier gain. And that's what this is saying, that the manufacturers, they don't tell you what the output offset is going to be, because they don't know what application you're going to be using operational amplifier. Instead, what the manufacturer will tell you is the input offsets are specified, right? That's what they will tell you. And the designer can use these values to compute the output offset that results in a particular application. So if you're going to be using it for the same amplifier for different configuration, network configuration, the manufacturer will not tell you what the output offset is going to be, because they don't know. Remember, the output is going to be dependent upon the gain times the input, right?
Yes, sir.
But what they will tell you is what the input offset condition is. Because it doesn't matter what your application is, your input offset is your input offset. Now, what are your input offset that they speak to? in a nutshell, gentlemen and lady, if there's any ladies, what happened is I want to get rid of, and I'm using again the analogy, I want to get rid of the water that was in the drum before I started to pour water in the drum, right? So I want to make sure that the drum is truly empty. So I have to get rid of whatever water was in the drum. So instead of actually piercing the drum, to get rid of the water, which is what you'll be doing at the output, right? I don't want to do that because it means that if I pierce the drum, the likelihood is that whatever I'm going to put in is going to run out through the pierced hole that I would have had in the drum, right? So
Yes.
what I have to do is go to the input, which is the opening of the drum, and try to do something. So I can go in there and bail the water out. Would that be that I use a suction valve or just flip the drum over? I'm going to the input, right? To change what is already in the drum. So that's what they're talking about when they say you can use input offset conditions to get your output to be zero when you have no input. There are two input offset conditions that every operation amplifier will come with that you can use to control, that you can use to cause the output to go back to zero. One such thing is the input offset current. So you can use current to offset to reset the output voltage back to zero. Or you can use input offset voltage. So two things you can use: input offset current and input offset voltage. What we did last week was input offset current, right? And just a quick refresher again in terms of what was done. So here we're talking about input offset. You remember this circuit? Remember this network? Figure 1022. All right, that's what we did last week, you know.
Yeah.
Anyway, let's go back through it quickly. Because the guys have to help me for helping you know. If you don't help me, I me just help myself. Why it you know in our pretty with Uno because remember saying you know, me have know this already. And me want you guys to come and know this thing too, because sooner or later me soon stop teaching and one of you guys have to take on the mantle. You understand? Who's ready to put them on up soon for start teach it?
Wait, what was that, sir?
Who is ready to take on the mantle to start 1, 2, 3? To start teach this course. Cause I say, you know, what I say is that sooner or later, you know, I probably soon can't teach this anymore.
Well, don't say that, no, sir. Come on.
So no, I'm saying it, and I'm saying it in a serious way because I want you guys to step up to the plate. That I can call on Mr. Robinson to fill my gap when I'm unable to do it anymore. Mr. Lewis to co-teach with me. As a matter of fact, I'm going to start introduce some of these things, you know. Students get marked to co-teach. So you're going to have to read the material, get familiar with the material to help me to teach. That's a plan for the next time. All right, so let's get back to Ms. Robinson not answering me. You don't want to step up to the plate to help me teach.
Hello? Sir?
Yes, ma'am.
Yes, sir. What did you say?
I mean, you didn't hear what I was saying before then.
I heard you said something about co-teaching, sir.
You should have heard your name called that you're gonna be helping me to co-teach. this module.
In the future, sir.
We have to start now. You have to learn it now, guys, in order to do that in the future.
Yes, sir.
All right, so let's get back to the presentation. So we said that there are two, there are two things that we can do to offset the
To the
offset the output voltage, right?
yes, sir.
Okay. We can actually, as I said before, change our the input current to remove that offset output voltage, or we can change the input voltage to remove the output offset voltage. So the first one is that, let's look at this one. I'm going to quickly go through it. This network, as in figure 1022, shows you how you can actually use the input bias current to offset the output voltage. In other words, to make the offset voltage be zero when you have a zero input voltage. If you observe the circuit closely, what is happening at both inputs?
Sir?
Sir, the inputs are 0.
Exactly. So if our inputs are 0, what must happen to the output?
It should also be 0.
And that's it. That's our intention. That's what we want. Okay? So in order to achieve this, what we do is a couple of things. Well, first of all, we know that both inputs are 0, but we know we're getting an output voltage.
Because of the offset value.
Right. That's the first thing. And that output voltage is going to cause a current to flow, a feedback current, right?
And then that feedback current is going to resist.
And that feedback current is going to cause a voltage across this, eh? But that feedback current is what we call the bias current. Because it is only true, remember what I said? It's only true biasing that you're going to have this. Remember? Remember I said when you bias the transistor, you're going to have electrons flowing, right?
Yes, sir.
Cool. So we call it the bias current. Now, just let's consider it as bias current for right now. Now, there's something that we also know. We know that this current is going to be coming right at this point. I will know something about this specific point. Oops. Sorry for my arrows. But this point, we know something about it. What do we know about this point? What is it called?
Virtual Earth.
Virtual ground, right? Virtual Earth. Which means at this point, what happens? The voltage right here is 0, right?
Yes, sir.
Even though it's not connected to ground or to 0 at this point. Okay. Now, if that's the case, yeah, it means that this is a virtual ground and there's a current that is going here. There's also going to be a current that is coming here as well, which is going to be the same current, eh? Because both of them are at ground, eh?
Yes, sir.
Yes, sir.
Cool. But what we know is that the current that is going to the inverting input is going to be called IB for bias current, right? For bias current. And it's minus because it's connected, it's going to the inverting input, right? And this one is IB plus because it's going to the non-inverting input. True?
Yes, sir.
Cool. But for this network, there is a new component that has been introduced, and that's called a compensating resistor, RC.
The one that's connected to the
non-inverting, right? So this is a new one that has been. So this would have been normally just a regular differential amplifier, right? with zero input voltages.
Yes, sir.
Good. But now we have a current that is coming. A resistor, sorry. That's right here. We know that if we have a resistor right here
That's
and a
current
resistor
we're
right
going
here, the truth be told is that we can actually, I use a different color, we can actually look at this in another way. We could actually say the current that is coming, the current that is here, the current actually is going in this direction. Let's assume the current is going in that direction. And it doesn't really matter because the assumption, remember, assuming current direction, nothing wrong with it. If you assume
Yes,
the
sir.
current is right, not the magnitude is what's important. The direction is not even important because we know that the current can be negative, right? We know that, right?
Yes, sir.
All right. A negative current just simply say that the direction that we assume the current is flowing from is actually opposite. It's flowing opposite to what we assume it to be. So the current is not negative. It's just that the direction that we assume it to be coming from is opposite to where it actually is coming from, right? So if the current is coming this way, so we have this as IB, so this is IB minus current that's coming this way. And this is IB plus that's coming that way. Just our assumption, instead of saying it's going into, this is B plus. Guys are following me so far?
It's sir, so both of them going to have the same. Okay.
All right, so we just assume the current is going that way. But one thing we know, and which is why we're making the assumption, is that a current times a resistor is going to give you what?
Voltage.
So you realize what happened?
Have the,
We didn't start with a voltage because the voltage was grounded. The inputs were grounded. So we didn't have a voltage. But because of this feedback bias current, and assuming the current is going in that direction, we now have a voltage that's going to drop across the resistor. And that is, in this case, across both resistors. So far, so good?
yes, sir.
So say all of us? I don't hear the choir singing.
Yes, sir.
All right. Now, if that's the case, we can then jump to figure 1023. I'm going to look at figure 1023 and figure 1024, starting with figure 10. Okay, well, this one says this is figure 1022A. 1022A. So we're not looking at even these as yet. We're just looking at the circuit. You realize that what is happening with the circuit is what I just said, right? In that, really and truly, the current flowing in that direction, and if you have a current source flowing across a resistor, then it gives you 10. It would give you 10. It will give you this network. So you move from here to here. Because everything else remained the same, only that instead of we representing the current flow that way, we're just basically saying that we're replacing that with a voltage source. So this here now gives us this voltage source here. Yes. What is that?
Oh, it's just like I represent. Okay, yes, sir. I was wondering what that was.
I want everybody to follow me, because I don't want to get confused. Everybody see how I got this? So remember I was saying current is flowing back in that direction from the diagram I had before. Because the current try 3, I'm not sure. A 2 then. Yeah. Make a note of it here. Okay. It's the same thing that happens for this. Let me use a different color. I'm not liking how you guys are sounding quiet, you know. You guys are making me worried. So what I'm doing, I'm representing this again as a voltage source. So it means that the current through the resistor is going to give us this voltage source right here. See? So remember, what is voltage? Voltage is I times R, right?
Yes, sir.
See, so if we represent this, we have I as I minus B and R as in R1. So therefore, the voltage V would be, so this is V. So V would be what? This V, let's call this V minus. V minus would be what? R1 times
R1 times R1.
Right. So in other words, we can call this right here our V minus.
Minus.
And similarly, we can call this here our V plus. But importantly, what is to note is what V minus and V plus is. Okay? Meaning that it's IB plus times RC, and this one is IB minus times R1. Okay? So this is a complete network now. This last one is a complete network with both voltage sources at the inputs due to our bias current. What type? Everybody say that before I move on.
Yes, sir.
Okay. Wonderful. Now, let's look at the network with let's ground. Remember now. So now we have two input voltages that we didn't have before. But if we want to find out what the overall output voltage is, we're gonna use superposition theorem, right?
Yeah.
Good.
Yes, sir.
So we have two input voltage. So let's look at it. Let's look at what each. So to superposition has taught us that if we want to know the output voltage based on two sources, what we have to do is ground one of the source, yeah, and apply an input voltage to one, right?
That's right. That's right.
And that's what is happening. And that's what's happening with this first one here. So if we ground, if we assume that there's no current, that is on the compensation resistor, a compensating resistor.
Okay.
It means that the output voltage would be a product of the input voltage time its gain, right? And if this is truly grounded, if you look at this network, you realize that this is what kind of network?
Which one's the fourth one?
We're looking at, make sure, because I want it to follow. We're looking at this one.
Oh. Wouldn't that be a different?
It would be what?
No, I was about to say wouldn't that be a differentiator, but then I realized no, because only the top part of.
So we're looking at this one. This is
Yes,
a
sir.
simple. This is a simple what? Inverted amplifier.
Yes. Because again,
Okay.
the top and the bottom is
Right. This is grounded. But this is as a voltage. No, this is a voltage. Now remember I said this one has a voltage?
Okay. Wait, but sir, before when both the inputs were grounded, it could have been considered a differential, a difference amplifier, right?
Actually, it would be a different amplifier that would be operating in the common mode configuration because both inputs would be
Grounded.
the same. That's why I want you guys to pick up the reason, eh?
Alright.
All right. So back to what we're saying.
Let's
This
see.
this circuit or this network would absolutely be an inverting amplifier. All right. So if it's an inverting amplifier, we know that the output voltage of an inverting amplifier
Minus
is its
RF.
input voltage time what?
Did I answer?
The output voltage for an inverting amplifier is the output voltage for any amplifier is this gain times input voltage, right?
Yes, sir.
Yes, sir. Yes,
So
sir.
we could say for this network, the output voltage VO1 would be what? The gain times its input, right? What's the gain for this network?
RF over minus RF over R1. RI.
Minus RF over R1. Yeah, that's the gain. And what would be the input? So can I remember it's the gain times the input voltage. What would be input voltage?
Going the other way, sir, would not be input voltage be minus R minus R1 minus IB times R1.
Yeah, it would be IB times IB minus. That's the input voltage now. IB minus.
Times R1.
Wait, that's sir. Wouldn't it be going like in the other direction, sir?
Forget about the direction. Remember, we established that already, man.
So that check, sir.
This expression now would be the output voltage for this network, knowing that this is our input voltage, and this is the gain of the amplifier right here. Is a gain. So it's a gain, and it's a gain because it's a gain for an inverting amplifier. This is an inverting amplifier, right?
Yes, sir.
Hence, the output for this network now would be this. Or you realize that the R's could cancel, right?
Yeah, R1 cancel out.
Cancel. Okay. So it means that this would leave you with what? V out then would be
RF IB minus.
RF minus RF
IB.
times IB minus. Remember, you have to keep that. That is important, right?
For IB minus, yes, sir.
IB minus. So that is the output voltage for this network. Okay? All right.
Yes.
That's one. The second would be to ground this one now and apply the voltage to this one, which is what happens in this network. You ground the inverting input, and by grounding the inverting input, we're gonna apply the voltage to the non-inverting input.
Sure.
We're
The
gonna
two
get.
ways that you were talking about, sir. These are both of them?
I'm
Or
sorry.
these are just the two you said there are two ways that we could that
No, man. This is just one way. This is just looking at the bias current.
Okay.
That's just the bias current alone we're looking at. We are looking at the voltage as yet. The input voltage. It's just one way. But the one way, what I'm trying to show you is that if we, and it goes back to this, I want you guys to, because I think you're losing it. This is a network we have,
Yes, sir.
okay? And if we have this network, and we add a special resistor called a compensating resistor, what we want to do with this compensating resistor is to use this resistor along with the bias current to make the
Get rid of the offset.
output zero, okay?
Yes, sir.
Cool. But we're saying that initially, if we ground this, the two inputs, which is what you want, nothing at the input. So if nothing is on the input, but we're still gonna get the output voltage. That's what happens in reality. And if we get an output voltage, it's gonna give us a feedback current. And that feedback current is gonna be available here. I will call this IB minus, and minus because it is an inverting input. And it's IB because you realize it's because of the bias current. Remember, we have no voltage at the input, so it's a bias current that's causing the current to flow, right? Meaning that you forward bias one junction and reverse bias the next junction. That's what you're talking about, bias current. When we do that, we know the current is going to flow internally of the transistor. And it's called a bias current. And because of virtual ground, the current that is here is going to equal to the same current that is here because both of them are at ground, eh?
Sir.
But this is called IB plus because this current now is going to be on the non-inverting input. But they're going to be pretty much equal. The other thing that we did was assume that instead of having the current going into the transistor, we say, okay, let's say the current is going out of the transistor, which nothing is wrong with that. We have been through all of that a while ago. Nothing is wrong with that because we're assuming the current is flowing into the transistor. That's our assumption. But the truth be told is that the current is going to flow this direction out of the transistor. You know why? Anybody want to? Let me see the brilliant who's going to tell me. 5 marks towards to add to your in-course test if you tell me why.
Repeat the question, sir.
The
That's
current,
why we go that way.
why are the current going in this direction? We can safely assume that the currents are going to go this direction instead of going this direction.
Sir, because of the characteristics of the op-amp, sir.
What does that mean?
Current flow into the input.
If the current going, you would have a massive gain, sir. Saturated gain.
Sir, you would say that current flowing into a junction will flow outside of a junction. So you can say that the IF is equal to IB plus IB naught. And also where the reference is located. So
Working hard for the marks, man. One last guess.
Yes.
Sir, can I give it?
Anybody, man. Anybody.
Okay, I think, not completely sure, but I believe that the current would flow that direction because it's going to it's flowing in the direction of the highest potential because in the direction that it's flowing towards zero, and the opposite direction has negative potential.
Okay.
Alright.
All right, let me tell you, because we're moving on. So nobody earned the 5 marks. So, tell me 3 of the main characteristics. Somebody mentioned it, but didn't say it. What 3 of the main characteristics of the
high input impedance of the op-amp, sir.
So if the amplifier has a high input impedance, what's gonna happen?
Sir, leave me 5 marks, please.
You're too late. You're too late. If it has a high input impedance, then definitely we can make the assumption that impedance is large here. So therefore, if a large impedance means current is going to flow to the path of least resistance. So the current, we can assume that the currents are going in that direction instead of going into and
Sir,
through the
sir-
amplifier.
Is
Don't worry about no yet. So we see why the current is coming that direction, right? So we see it. And the other easy thing to think is that it cannot be that the current is, assuming the current is going in that direction is incorrect. Because anywhere you assume the current is going, it doesn't matter, because we cannot have a negative current. Remember we established that a while ago? We're not going to have a negative current. All we're going to have is that if we assume the current is flowing in one direction and actually see the current being negative, it just simply means that where we had assumed the current was flowing, the current is actually flowing in the opposite direction. That's all a negative current means. That you should have established a long time ago, from even before they did networks. From physics days. Or any form of electrically related science that you would have done. By the way, since we know that a current flowing in that direction and it's flowing across a resistor is going to give us a voltage, right? Yes?
Yes, sir.
So we established that what's going to happen is that we're going to have a voltage due to that and a voltage that's going to due to the current here. So the voltage in this case is IB plus times RC, and the voltage in this case is going to be IB minus times R1. Am I correct?
sorry, sir, my Wi-Fi just tripped out. What was the question, sir?
If the current, if we have a current flowing in that direction and that direction, as we assume, then a current flowing through that in that direction is going to flow through R1. And a current
Okay.
flowing through R1 times R1 is going to give us a voltage. I would say that this voltage would be V minus. And this one is going to be V plus.
Yes, sir.
And V minus would equal to what? You tell me. Quickly, what V minus is.
B minus times
IB minus times R1, sir.
IB minus times R1.
R1. That's
Brilliant. Don't want to lose you guys, you know. This is not critical, but we don't want to lose you.
Just
guys.
let me know I lose the 5 marks, sir.
Oh, talking about that, sir, sir, you fight me out, sir. One of the characteristics is that it doesn't allow current flow through it, sir. What, sir? Sir.
One of the characteristics. There are 3. There's actually 5 or 6. But there, so you say when you say one of the characteristics, it could be anyone. You'd have to be more specific, you know.
Sir.
Anyway, so this one now is gonna be IB plus, right?
Plus?
IB
Oh, yeah,
plus.
IB plus. Yes, sir.
IB plus times RC.
Okay, times RC. This was a student they love teaching them. All right, so if we know that, ladies and gentlemen, we can simply now start to look at some things. And I'm not even going to the next page because I realize that you guys are stretch and stress the things when I need to. No, if that's the
Oh,
case.
wait, no, I think because of this, sir, is because I just started saying, you said that the manufacturers had one of 2 ways to combat the off.
So
Sorry.
we're looking at only one right now, which is which has to do with IB, which is what is called bias current. Okay,
Okay.
it's
Oh,
IB.
no, yes, sir. That's no, and then that led to my realization that there's two sub parts underneath this one main part method.
All right, absolutely. So now what happened is that because of this, these two currents now that are at your input, which you never had in the first place because they were grounded, but you only have them because of the bias current that has been fed back. Now you have a voltage at both inputs. You clear to see that?
Yes, sir.
Cool. Now, because we have two voltages rather, at the input, and we have one output, it means that the two inputs are going to be contributing to the two input voltages are going to be contributing to the one output voltage, right?
Yes, sir.
And in order to find what each input is contributing, we wouldn't have to use superposition theorem. Agree?
Yes, sir.
All right.
Yes, sir.
So now using superposition theorem, sorry, it means that we're going to have to ground one of the input voltages and apply one. So if we ground, and let me just use this note to make sure that you guys are following me now. So if we did this, if we say, okay, let's ground, so let us apply no voltage on the non-inverting input and apply this V minus only to this network. You'd agree with me that quickly the circuit would look something like this. This is positive, this is negative, this is VO. Sorry. But this will be VO, I will call this VO1 because we're going to apply our voltage 2 here. And the voltage that is being applied here is happening naturally. This is our feedback. Oops. Oy, oy, oy. So this is V minus. And this is R. Oops. This is R's. Oops. Shut. This is R1. And on this side, of course, we're going to have RC, but this is going to be grounded. So no voltage is going to be applied here. And this is RC. So agree with me that using superposition, this is what you would get, okay? This will be the resulting network for your output voltage, applying your input voltage to the non-inverting input. Sorry, the inverting input for starters, right?
Yes, sir.
Yes.
Good. If that's the case, we know that this is a non-inverting amplifier configuration. So we know the gain. What's the gain of the non-inverting what's the gain for the non-inverted amplifier?
Sir, you said none. Sir, where you said the input is being amplified, sir?
For the invert, my apologies. For the invert, what will be the voltage? What will be the output voltage?
Minus over R1.
Write it down below, sir. Oh,
It would be VO1 equals to what? The gain of the amplifier. What's the gain of the inverting amplifier?
Negative RF over R1, sir.
Minus RF over R1. That's a gain. And what times the input voltage? What's the input voltage?
IB minus times R1.
V
V minus, which is
IB minus
R1.
That'll be V minus.
V minus, which is,
without
and those for ease of seeing, R1 times what?
IB.
IB
minus.
IB minus.
and then have a cancellation.
Our R1s are going to cancel, right?
Yes, sir.
All right. Woo. So you guys make me take so much idiot man for understand the little thing, man. So therefore, those cancel. So our output VO1 would simply be what? Oh, it's a different color.
Minus RF times V minus.
Here we go. There we go. There we go. So that this is going to leave us with minus RF
IB minus.
times IB minus. So this is what would happen. This is VO1. Right? Now, if we, so that's us one. Remember, that's us one. If we should change this network, and then we draw the network now, the same network, but we ground this one. Not for the next 10 days. So here, we have R1, oops. We have RF. We have our output voltage. It's going to be, in this case, VO2, right? R1. R1. RF. But this is grounded. And this is the one that we're going to put our voltage on now. Right. This is RC, and this is our input voltage. V plus, right?
Yes.
Okay. So this is grounded. So therefore, it means that this configuration would be a non-inverting amplifier, right?
Yes, sir.
And we know that they gain for the output voltage in the VO2. So VO2 would be again the gain times input, right? But what's the gain? But this is a non-inverting amplifier. What's the gain of a non-inverting amplifier?
1 plus RF over RC.
1 plus RF over RC over, in this case, right? RF.
Times input.
That's the gain. So it's a gain times what? Times the input voltage, eh?
Yes, sir.
The input voltage is V plus. And we know that V plus is what?
IB plus times RC.
IB plus times RC. All right, oops. Oh my word. supposed to be RC. So therefore, what would be our output voltage? Since you know this, what would be our output voltage? Simplifying this expression.
So you'd have been
Just make sure.
1 plus RF times IB plus.
All right. All right, so we're gonna simplify, but at the end of the day, for the complete network now, we know that VO, we can call it VO total, VOT, from what we just found would have been what? VO1 plus VO2, agree?
yes, sir.
Okay. So that's what it would be. VO1 plus VO2. We know what VO1 is, we know what VO2 is. Yeah? So we can put them together. That's all of this was saying, you know. We can now put them together and find what the overall, because of superposition theory, when we have both input voltages, like on this, we can put it together and find what would be the overall output voltage of this network. So that's why we get that the output voltage, yeah? Whew. So we're on this page where we said combining equation 10 for the 1 and equation 10 for the 2, which is really superposition, right? We obtain a total output offset voltage due to bias current, which we designate by saying VOS, which is the output offset voltage due to the bias current, which is in bracket. So VOS IB equals to the combination of the two expressions we just have a while ago. See, minus IB minus times RF, right? Which is what we got before, right? Yeah? So don't mind the minus here. Don't mind the minus. It's the same thing. Plus this, which we have a while ago. All they did in this expression was just turn them around. You realize? Multiply both by -1. So this become a positive, right? And this become negative. Because remember, this is positive here, right? This is positive here, eh? And this is negative here. So when they group both of them, that's what they got. Makes no difference. The same expression. This is what we get when we superimpose both, eh? All right, am I clear?
Yes, sir.
Yes, sir.
Good. Nice. Now, from this, remember what our main objective was to do? Our main objective is
Put
to
it to be 0.
get rid of the VOS.
Yes, sir.
What's the main
So
objective?
put it to 0.
No, we can do that by doing a couple of things. Remember, initially we said that we have IB minus and IB plus, right? IB minus, we have IB plus. And we said that if we assume, based on, and again, a good assumption, if both are equal, if they're the same, then we can basically group them and say, okay, let's call this IBB then. It just means the bias voltage on both inputs. That's what it means. Bias voltage on both inputs. So all we're doing is just make IB equals to IB plus equal IB minus, which is going to equal to IBB. And if we do that, we can replace IB minus IB plus in this equation by IBB. Body follow that? So we can replace these two by IBB. Simple maths, nothing, we haven't breached anything as yet, right? So like you guys gonna sleep.
Yes, sir.
All right. So if we haven't done anything, we just put back that, we just replace IB minus with IBB and IB plus with IBB since both are equal. And if we do that, it means that we can simply factor out IBB out of this equation. Because we have IBB here and IBB here. And we just factor out IBB. So if we factor out IBB, we'd have IBB out of the front times RF. So IB minus is IBB times RF minus 1 plus RF over R1, which is what is here, times RC. And then IB plus is also IBB. So it will be coming right here. So it means that we could have this big expression with IBB. And if that's the case, ladies and gentlemen, we're in business. Because it simply means that,
Sir?
yes,
No, I was saying, no, sorry, no, go on, sir.
right. What we're trying to do is to make this 0. Remember, that's the game. That's a game, right? We want this to be 0. If we have an expression, so that's what we want. If we have an expression of two products, to make this become 0, it means that one of the product must be, you can make one of the product be 0 for this. One of the variable in the product be 0, right?
Yes, sir.
Now we could either make RF be 0 or the entire or all of this being 0. Now we couldn't make IB be 0 because IB is a natural current that's going to be flowing due to biasing. Remember? IBB couldn't be 0. RF couldn't be 0 because if RF was 0, what would happen is that we would not have a
resistance in the feedback.
okay, and that means that we'd basically be operating as a voltage follower. And therefore there will be no gain. Remember?
Yes, sir,
Remember?
yes, sir.
Right. If RF over R1 is for the minus RF over R1 is gain for what? The inverting amplifier, right?
Oh,
And if RF was 0, then it means the gain will be 0. And likewise, the same thing for the non-inverting amplifier. It means that the gain will be 1. So it means that there will be no gain if RF was 0. So we can't make RF be 0. So the only thing that can be 0 is the expression here. So not RC, this expression. The expression, this. Okay, because it's this times this and this times this. So we say if we make all of this part, I'm sorry, not this part, all of this part.
As in the entire bracket.
Everything in the bracket be 0. If we make all of the thing in the bracket be 0, all of this, that means 0 times IB would make this become 0, right? True? If we make all of this in the bracket become 0,
Yeah, yes, sir.
then it means that 0 times whatever the current is it would make the output offset voltage be 0. So what is done is to make is exactly that. Make RF minus all of this equal to 0. And if that's the case, it means that mathematically we're saying that RF minus 1 plus RF over 1 times RC equal to 0. Solve this expression. For this expression, let's see what this expression is saying. Expand this expression. First thing to comment is that we can bring all of this over this side. Agree? So we can say that from this expression, again, shouldn't be doing this enough because you guys are supposed to be steep at analyzing in terms of at this level. So we could say that RF equals to what? 1 plus RF over RC times
RC.
Times RC, right?
Yes, sir.
That's what we're saying. RF equal to that. Now, if that's the case, it means that again mathematically we'd have to simplify this for it to make sense. Okay, you can have RF equal to something RF again, right?
Yes, sir.
Don't forget RF from 7.
Okay. So the first thing that we could do is what?
Expand the multiply everything in the bracket by RC.
Okay. So we say RF equals to RC. RC plus R plus RF. No, sorry.
RC.
My apologies. Let's check. This is not
That's R1.
This is not RC, this is R1, right? Make sure we do it right. R1. So this would be RC plus RF RC over 1, right? RC over R1 rather.
Yes, sir.
RC R1. And all of that equals to RF. Okay? Now, again, what is our game? Bring RF over on one side, right? So this would be what? RF. We bring this part over here. What we get?
Minus RF RC all over R1.
And this equals to
RC.
RC. Now, if that's the case, oops. Let me see how much of a primary school you guys are making. That is going to be over 1, right?
Yes, sir.
Okay. I mean, I'm doing this, but we could have do it another way. We could have factor out RF, right?
Yes, sir.
Yes, sir.
So we could have RF into 1 minus
RC over R1.
RC over R1. That's not helping us. RC over R1, right? And that's equal to RC. Cool. So therefore, if we want to find RF,
Divide both sides by the bracket.
divide both sides, right? Okay. No, actually, that's not what I want. What we really want, I should probably let me change it from here. Let me backtrack a little. Okay, let's do it again. So from this expression, sorry, we want RC to be the subject of the formula. RC.
Okay. Yeah.
Okay. So if we want RC to be the subject of the formula, from right here we could say RC into what? 1 plus
RF over R1.
RF over R1 equals to
RF.
RF.
Mm,
Okay. So we want RC to be the subject of the formula, which means that we'll have to do what?
divide both sides.
Divide both sides by?
1 plus RF over R1.
But before we do that, to make our life a little bit easier, it could make our life a little bit easier. We could actually in the bracket here,
Make it
this
one.
small expression, right?
But R1 over R1.
Right. So this would be 1 over 1 over 1 plus. Yeah, I know you guys are smart, but I don't want to get some people lost over R1. So we're going back to basic school, primary school. The LCM would be what?
R1.
1 into R1 is R1 times 1, right? Plus R1 into R1 is
0, 1.
it'll be RF, right?
Mm-hmm.
What we get from the bracket here is this. Yeah? Agree?
Yes, sir.
Times RC equals to RF. And now that that is the case, we can bring this part over here now, right? Divide both sides by all of this. So,
Mhm.
RC equals to what?
RF times R1.
RF. Let's make it first. RF divide by
R1 plus RF.
R1
Sir, don't forget the R1 in the denominator, in the numerator.
plus RF all over
R1.
R1. Okay. Mathematically, how you simplify this now? This.
Times R by the reciprocal, sir.
Reciprocal. You remember I said primary school thing this, remember? So RC is going to equal to what? Oops, RC. This. You guys should be trumping a bit to tell me this now. RC is going to equal to what?
R1.
RF.
R1.
Well, I could put it another way. RF over R1 plus RF, right? Times what?
R1, sir.
Times R1. Okay. All right. Out of this expression, what do we have left?
Sir, what you mean, sir?
You don't see what we mean. What we mean is this. This is what? RF times R1 over RF plus R1.
Oh, product over some, sir.
You know, see that? But it's not only product over sum. It's something else that you should do. RF plus R1. Would you agree with me that this is what RC is?
Oh, one.
Would you, first of all, would you agree with me that this is what RC is?
Yes,
Yes.
sir.
Okay. What does that tell you?
Resistance in parallel.
Exactly. RC equals to RC actually equals to RF parallel R1. Everybody see that? RC from its expression. Remember, parallel resistor is the product of the resistor over the sum of the resistors, right? That's what parallel resistors are, right?
Yes, sir.
And that's exactly what we have. RC is. RC is RF times R1 over RF plus R1, which means RC equals to the parallel combination of R1 and RF. So that's what this is telling you. RC equals RF over R1 plus RF. RF over R1. RF times R1 over RF plus R1, which means that RC is a parallel combination of RF and R1. Make sense?
Yes, sir.
All right. So, if that's the case, going back to the big expression, this expression, I can erase some of these now because you understand some of these terms. So, you can. Remember what we say? We said that VOS equals to this minus that, right? And if we make this part be 0, make this become 0, it means that VOS due to IB is going to be 0. To make this part become 0, it means that we have to make RC parallel R1. Sorry, RF parallel R1. That's the only way RC can become 0. And not RC. That's the only way what's in the square bracket here can become 0. Or if what's in the bracket here is 0, then RC equals RF parallel R1. That's what it's saying. Okay? So you see why it is now a compensating resistor? Because we realize that RC, once we set RC to be RF parallel R1, it makes this function here become 0. And if this function becomes 0, the offset voltage here becomes 0. Simple as that. You see that?
Yes, sir.
Cool. Also, lastly, if we should put back RC in the original expression, so note expression 1046 right here. 1046 comes from the original expression, which is this one. So let's erase this to clean up this so we can see. 1046 is coming from 1043. By just simply placing RC in the equation as RC equals to what? RF parallel R1, right? So VOS equals to what? IB minus times RF. So look at equation 46. VOS IB equals to IB minus RF. Nothing changed there, eh? Between equation 46 and equation 43. Agree? However, so I put back this again in a bracket. Again, this don't change between equation 1043 and 1046. And 43, right. When we expand this bracket, you'll agree with me that this is going to be IB plus times RC. IB plus times RC. What is RC? RC is what? R1 parallel R2, right? RF parallel R1. So we're just putting back that. That's going to expand this part, expanding the equation. So when we expand this times that give you, and then we're making RC becomes R1 parallel R1 parallel RF. And then we'll go also multiply this by this, which is what happens next. When we multiply this by this, because RC is R1 parallel R1 parallel RF, this is what you're gonna get. So when this expression is now simplified, you will see, ladies and gentlemen, that this is gonna go with this. Yeah? And R here is gonna go with this R. So what do you have left? IB minus times RF minus IB plus times RF. So it means that you can factor out RF out of it. And this is what your VOIS equals to. Simple as that. Now, right now, that's the case. So like I'm losing you guys.
No, we're here, sir.
Okay. Now if that's the case, it says equation 1046 shows that the offset voltage is proportional to the difference between IB plus and IB minus when RC is the parallel of R1, R2, of R1 and RF. You follow that? This come from all of what we're doing, you know.
Yes, sir.
Right. And this, of course, is so simple that the difference between these two. And doesn't matter which one is bigger. But if both are equal, which is one of the conditions we assumed before, if both are equal, then what? Then it means that VOS is going to be
0.
exactly. So it shows that, and that's what all of this is saying, is that because the inputs are usually reasonably well matched, the difference between IB plus and IB minus is quite small, if any. All right, so let's say that they're a bit different. It can be different, because remember they're passing across different resistor value, right? R1 as opposed to RC, right? But R1 does not necessarily have to be equal to RC. So the current, the bias currents can be different, but they are not much in terms of difference. Now, it continues to say that the equation confirms the fact that the output offset voltage is 0 if IB plus is equal to IB minus. So if both are equal, then it means that in other words, your compensation resistor would have equal to your R1 input resistor. Also, your output offset voltage due to the bias current may be either positive or negative depending on the value, whether or not the IB plus is greater than IB minus or vice versa. Unless actual measurements are made, we rarely know which current is larger. So a more useful form for equation 1046 is to say that the modulus, you know what we say taking the modulus now? The modulus of the offset voltage, can you remember I say voltage can be negative, right? So the modulus of the offset voltage is equal to IIO times RF, where IIO is a modulus of the current, the difference in the current. So if the two currents have a difference, then even though we make this assumption that IB plus minus IB minus, it will make a difference if IB minus is greater than IB plus, because the modulus is going to give you a positive answer. Agree?
Yes, sir.
Cool. And so now, we could actually write the expression in this way. The same expression, you know. The same expression, this expression could be written in this way. Right? This way. If the currents are different. If the currents are equal, then it's fine. It means that we're achieving our objective because we're making this be 0. But if they are different, slightly different, this is a better way to write the expression, which just show you that IIO is really the modulus of the two current. If they're the same, then you realize that it works out to be the same, right? Because if they're the same, 0 minus 0 is going to be 0, right? But if they're different, doesn't matter which one is greater, IIO is going to give you a positive value. But, ladies and gentlemen, it doesn't matter whether or not we get the modulus of VIOS. That doesn't make a difference, because if you have a negative or a positive VOS IB rather, it simply means that we're still gonna have an offset voltage. And remember, I try to get rid of it, right? So here it says equation 1047 shows that the output offset is directly proportional to the value of the feedback resistor. That's what this is saying. For this reason, small resistance value should be used when offset is a critical consideration. However, to achieve large voltage gain when RF is small may require impractical small values for R1. And to this end, or to this extent, that the amplifier may overload the signal source driving it. So what they usually do is it says in any event, a large closed loop gains are determined by another aspect of output offset, as we will see in a forthcoming discussion, right? Which is the next one, right? Next one coming. Now I said two conditions, right? So in the next condition. Here, last thing, ladies and gentlemen, last but not least, remember this is critical. Another common manufacturer specification is called simply input bias current. So they don't call it IB minus or IB plus, they just call it IB. It refers to either or both IB plus and IB minus. By convention, what they do when they say IB, they find an average for both IB plus and IB minus, right? So IB is taken as the average of IB plus and IB minus, which is what this is. And they say IB is typically much larger than IBO. Because remember, IBO is the difference, while the IB is the average, right? Because IB is on the same order of magnitude as IB plus and IB minus, while IIO is the difference between the two. It is important to know that IIO is normally given by the manufacturer as a maximum value, meaning that it can actually be between 0 and the published value. So when I give you IIO, it's a maximum value. And therefore, the term VIOS equals IIORF should be taken as the maximum worst case value. Am I like that? Therefore, VIOS IB equals to that should be taken as the maximum worst case value. What does that mean? It means that when you're finding the offset voltage due to bias current, if you're using this as a way to find it, it means that you're going to have to assume that this is the worst case scenario, meaning that's the highest offset voltage you're going to possibly have. Because remember, IIO is what? Let me see if you can remember. IIO is
Current offset, sir.
IIO is going to be IB, assume IB plus minus IB minus. And in that case, it is assumed that the currents are not equal. See it up here now, we just see it a while ago, you know. See? And we take the magnitude because we want to make sure that you don't have negative current. That's what IIO is going to equal to. So here's an example. A quick example. And I'm not going to work the example. I'm going to allow you to go through it because it's worked out for you. And you come back next week and tell me, well, next week I test it, I'll come back and tell me. You tell me on the chat or in the classroom if you do not understand it. But it's very simple. They give you the figure 1025, which is this. They give you the value of R1 and RF. They didn't give you the value of RC, but we know we can find a value of RC. That's going to make your compensation, that's going to make your this be 0 by finding RC to be the parallel combination of these two, right?
Yeah.
Cool. So they said that the specification for the operational amplifier in figure 10 states that the typical input bias current is 80 nanoamp and the input offset current is 10 nanoamp. So you know IB, I know IIO, input offset current. And for that, they say you must find the optimum value for RC. Remember, and this is the solution now. The optimum value for RC is where RC is going to cause what? The offset value to be 0, right? So RC must be R1 parallel RF. That's the first thing. That's what they give. That's what you find here. The second thing is they find the maximum output offset. The maximum output offset voltage due to the bias current when RC equals to its optimum value. So you know what the optimum value of RC is already, and they say you want to find the maximum offset voltage. Remember I said that maximum offset voltage occur at the worst case condition occur when this equals to IIO RF. What is IIO? IIO is IB plus the modulus of IB plus minus IB minus. But they gave you what IIO is already. IIO was given as 10 nanoamp. So if you want to find the worst case condition, it's just 10 nanoamp times RF, which was 100 kilo ohms. That's why you get 1 millivolt, which is the worst case condition. And then they want you to say, assume that IIO is 10 nanoamp and IB plus is greater than IB minus. So it tells you that IB plus and IB minus is not equal. And I want you to find the value of the output offset voltage when RC is 0. And this is what happened to make RC equal to 0 in equation 1043. You know what equation 1043 is already. See it up here, so if RC is 0, it means that if RC is 0, it means that this is what happens. Okay? Still there?
Yeah, we're here, sir. Well, I'm here.
Yes, sir. Still a room, sir.
Right. Here's the tricky part now. Here's the tricky part. Because RC is 0, and we only have IB minus from 1023, IB minus times RF, IB minus times RF. We don't know what IB minus is. We don't know what IB plus is. But what we know is what? We know IB, and we know IIO. What is IIO? IIO is IB plus minus IB minus modulus. What is IB? IB was given in the equation. IB is, see there, IB is IB plus IB minus over 2. And we were given, this was given in the problem. This was given as what? 80 nanoamp, right? So if that is 80 nanoamp, 80 times 10 to the minus 9, and you were given IIO rather, to be 10. And what is IIO? IIO is no. IIO is what? Come on, guys. IIO is the modulus of IB plus minus IB minus.
Yes, sir.
Cool. So there are some things that it's telling us. So we can find the average and the difference. So the average and the difference we know. So you have to know, make the equation to equate those two. We know what IIO is. IIO equals to 10 nanoamps. But more importantly, ladies and gentlemen, we know that this actually equals to what? IB plus minus IB minus. and that equals to 10. Okay? Everything is in nanoamps, so we'd have to write it back.
Okay, yes.
And we know that IB equals to the average, which is IB plus IB minus and divide by 2. And we know that that actually, from what was given, that actually equals to what? 80. 80 nanoamp. So you realize that, which is saying that I plus B plus I equals what?
Yeah, 160.
All right. Equal 160. Okay. So this is where a lot of common sense is going to come in now. So if this is 160 and this is 10, the sorry. If the sum is 160 and the difference is 10, how do you find them? How do you find them individually?
Find two numbers, sir. When you add them, you get 160.
Simultaneous equation, sir.
Yes, man. So that's where I'm going to leave it with you guys. You must be able to figure out that little part, because that is not devices, you know, that's simple maths, right?
Yes, sir.
Right. So it's simultaneous equation. So the sum equals to 1/6 and the difference equals to
85 and 75, sir.
absolutely. It's there in the answer. But what I wanted to do is, instead of you guys getting flabbergasted over, well, how comes you get them answer there? You can actually help yourself. So simultaneous equation, right away you can even add them. This become 190, 170. 170, we get rid of this. So IB, 2IB plus equals to 170. That means IB plus is going to be equals to 85, right? And if you know one to be 85, and it says you can identify the other one, right? Based on the simple maths. That's how they work. That's the solution to this. That's the solution to the problem. Next time we meet outside of the test, we look at the offset voltage, how the offset voltage actually can be used to minimize or get rid of the input offset voltage, get rid of the output offset voltage. That's what we're going to be looking at next class. Any questions?
Night, sir.
Night, Mr. Thompson.
Sir, did you mention what periods we're going to be doing the test next week and what topics? I guess I joined late because I had that.
Yeah, no, he didn't mention that. Yes, sir. What time for both classes? Because I know sometime Monday group doesn't have their class on the Monday exactly.
We have the test Since you're here Thursday, we have a test next week Thursday at 5 o'clock. We start actually at 5:30. It's an hour and a half test.
Oh, okay. And how we going to upload it, sir? The same PDF scan and
Yep.
onto okay.
Mm-hmm.
Sir, could you tell us what topics we're going to go for it?
Everything we do so far. We actually are behind in the class. Well, everything we do so far. That's it.
Yes, sir.
All right. Have a good night, everyone. I'll send you a post to you guys the recording as well. All right, for the class. Have a good and safe weekend. Safe stuff. All right.
Sir.
All right. Take care.
Same to you.
Bye bye now.